For decades, astronomy textbooks stated a definitive rule about the most extreme objects in our universe. They taught that black holes were the ultimate cosmic traps, regions of space where gravity was so absolute that nothing, not even light, could ever escape once it crossed the threshold. This certainty defined our understanding of the abyss for generations. It was an absolute law of physics. That assumption was wrong. The correction did not come as a sudden discovery through a telescope, but as a quiet realization in the mathematics of quantum fields. The truth is that black holes are not eternal vaults. They leak. They breathe out a faint, ghostly glow of radiation that slowly strips away their mass over unimaginable eons. This means that every black hole in the cosmos is destined to shrink, to fade, and eventually to vanish entirely from the fabric of spacetime. To understand how this happens, we must first look at the scale of the mystery. We are dealing with objects that defy our daily experience of reality. In our world, things have surfaces. A table has a top, a planet has a crust, and a star has a photosphere. But a black hole is different. It does not have a surface made of matter. Instead, it possesses a boundary called the event horizon. The event horizon is not a wall. It is not a physical membrane or a shell of energy that you could touch. It is a mathematical dividing line in the geometry of space itself. Imagine a river flowing toward a waterfall. If you swim slowly, you can move upstream and escape. But as you get closer to the edge, the current accelerates. Eventually, you reach a point where the water is moving faster than your maximum swimming speed. Once you cross that line, no matter how hard you struggle, you are carried over the edge. In the case of a black hole, the current is gravity, and the maximum speed is the speed of light. The event horizon is the exact distance from the center, where the escape velocity equals the speed of light. Since nothing in the universe can travel faster than light, anything that crosses this boundary is causally disconnected from the rest of the cosmos. For a long time, this was seen as the end of the story. Once something entered, it was gone forever, contributing its mass to the singularity at the center, leaving no trace behind except for the increase in the black hole's size. But when we look at a black hole from the outside, we are not seeing the horizon itself, because the horizon is invisible. We see the chaos surrounding it. We see the accretion disk, a swirling maelstrom of gas and dust being pulled inward. This matter is accelerated to relativistic speeds, rubbing against itself in a friction so intense that it heats up to millions of degrees. It glows with an amber and golden light, casting long, warped shadows across the void. We see the gravitational lensing, where the massive weight of the black hole bends the light from distant stars behind it, creating shimmering rings and distorted arcs. We see jets of plasma being launched away from the poles at nearly the speed of light, though these are born outside the horizon, fueled by the magnetic fields of the spinning disk. These observations give us a map of the perimeter, but they tell us nothing about what is happening at the very edge of the abyss. To measure something that emits no light, we have to stop looking for traditional signals and start looking at the vacuum itself. In classical physics, a vacuum is simply empty space. It is the absence of everything. But in the realm of quantum mechanics, there is no such thing as true emptiness. Space is not a void. It is a sea of activity. Even in the deepest reaches of intergalactic space, where there are no stars and no gas, the vacuum is humming with energy. This is known as the quantum field. According to the laws of quantum uncertainty, energy can fluctuate spontaneously. In these fluctuations, pairs of virtual particles are constantly popping into existence. A particle and its antiparticle appear together, exist for a fraction of a second, and then collide and annihilate each other, returning their energy to the vacuum. This happens everywhere, every billionth of a second. in every cubic centimeter of the universe. Usually, this process is invisible because it is perfectly balanced. The particles vanish as quickly as they appear. But when you place an event horizon into this sea of quantum fluctuations, the balance is broken. In 1974, Stephen Hawking began to examine what happens when these virtual pairs emerge exactly on the edge of a black hole's boundary. He realized that if a pair of particles appears right at the event horizon, it is possible for one particle to fall inward while its partner remains outside. In a normal vacuum, they would have found each other and vanished. But here, the gravity of the black hole acts as a wedge. The particle that falls in becomes part of the black hole's mass. The particle that stays outside, however, is now alone. It no longer has a partner to annihilate with. To the distant observer, this lone particle appears to have been emitted by the black hole itself. It escapes into space as real radiation. When Hawking published his initial findings in the paper titled Black Hole Explosions, the scientific community was stunned. The idea that a black hole could emit anything was an affront to everything they had been taught about general relativity. For years, the consensus was that gravity was a one-way street. Hawking's work suggested that there was a leak in the system. The reaction in the academic world was not immediate acceptance. There were long periods of silence and skepticism. The mathematics were dense, involving the complex intersection of quantum field theory and curved space-time. Many physicists felt that Hawking had made a mistake, or that the effect was too small to be meaningful. But as the calculations were scrutinized, the logic held. The room went very quiet when it became clear that the radiation wasn't just a mathematical quirk. It was a fundamental property of any object with an event horizon. This meant that black holes had a temperature. In physics, anything with a temperature must emit radiation. By linking gravity to thermodynamics, Hawking had bridged two worlds that had previously been kept separate. This discovery fundamentally changed the anatomy of the black hole. The event horizon was no longer just a point of no return. It became a site of active exchange. While matter and light continue to fall in from the accretion disk, a tiny, steady stream of particles is leaking out. This process is incredibly subtle. For a massive black hole, the radiation is so faint that it is completely drowned out by the cosmic microwave background, the leftover heat from the Big Bang. If you were to float near a supermassive black hole, you would not feel any warmth from this radiation. It is far colder than the deepest reaches of space. But on a cosmic timescale, this leak has profound consequences. Because the particles escaping into space carry away energy, and because energy is equivalent to mass, the black hole must lose weight. The more it radiates, the smaller it becomes. The event horizon slowly contracts. This is the process of evaporation. It is a slow-motion disappearance that takes place over timescales that dwarf the current age of the universe. For a black hole with the mass of our Sun, the process would take roughly 10 to the power of 64 years. To put that in perspective, the universe is only about 13.8 billion years old. We are currently living in the blink of an eye compared to the lifetime of a black hole. Yet, the fact that it happens at all changes everything. It means that the black hole is not a permanent fixture of the universe. It is a transient object. It has a beginning, a middle, and an inevitable end. The very things that make a black hole seem eternal, its crushing gravity and its absolute darkness, are actually the drivers of its eventual demise. As we contemplate this, we have to consider the physical reality of the horizon again. If it is not a wall, but a boundary where quantum effects can pull particles apart, then the horizon is more like a filter than a door. It allows certain things to happen while forbidding others. The classical view told us that everything crossing the horizon was lost to the singularity at the center. But Hawking's radiation suggests that the black hole is slowly returning its energy to the universe. This raises a question that has haunted physicists for decades. How far back into the cosmic morning can we actually look if the evidence of the past is being evaporated? If a black hole consumes a star, it takes in all the information about that star, its chemical composition, its rotation, the specific arrangement of its atoms. In classical relativity, that information is crushed and hidden away forever. But if the black hole eventually evaporates completely, what happens to that information? Does it vanish with the black hole, or is it carried away by the Hawking radiation? If the information is destroyed, it violates one of the most sacred laws of quantum mechanics, the principle of unitarity, which states that information can never be truly lost. If you burn a book, the information in the pages is scattered into ash and smoke. But in theory, if you could track every single atom and photon, you could reconstruct the text. But if a black hole evaporates and the radiation it emits is purely thermal, meaning it is random and carries no memory of what fell in, then the information is gone from the universe forever. This conflict creates the black hole information paradox. It is a war between general relativity, which describes the very large, and quantum mechanics, which describes the very small. The event horizon is the battlefield where these two theories clash. To understand the scale of this tension, imagine the vastness of the space surrounding a black hole. Outside the horizon, we have the laws of physics as we know them. We can measure the orbit of stars, the temperature of gas, and the curvature of light. But as we move closer to that invisible boundary, the rules begin to shift. The event horizon is the ultimate causal boundary. It separates the universe into two regions: the region where you can still influence the outside world, and the region where your future leads only to one place: the center. When a particle of Hawking radiation escapes, it is essentially a messenger from the edge. It tells us that the boundary is not absolute. This leakage happens because of the way spacetime is curved. Near a black hole, space is stretched so violently that the vacuum itself is distorted. The virtual particles that usually vanish are ripped apart by the tidal forces of gravity. One is swept into the abyss, and the other is flung outward. This isn't just a quirk of small black holes. It happens to every single one, from the tiny primordial ones that might have formed in the first seconds after the Big Bang to the behemoths at the centers of galaxies. The key detail is the relationship between mass and temperature. In our daily lives, we think of massive things as having more heat capacity, but Hawking radiation works inversely. The larger a black hole is, the colder it is. A supermassive black hole, millions of times the mass of our sun, has a temperature that is almost absolute zero. Its evaporation is so slow that it is practically non-existent for now. But a small black hole, one with the mass of a mountain or a small asteroid, would be incredibly hot. It would radiate energy violently and rapidly. Such a black hole would not linger for eons. It would end its life in a brilliant, explosive flash of gamma rays and high-energy particles. This means that the universe contains a hidden clock. Every black hole is counting down. The larger ones are ticking so slowly we cannot perceive it, while the smaller ones are rushing toward their end. This creates a cosmic cycle where the most dominant forces in the universe are actually the most fragile over the long term. When we look at the images provided by our modern telescopes, we see the black hole as a predator, consuming everything in its path. We see the accretion disk and the jet of plasma, and we think of an entity that only takes. But the mathematics of 1974 tells us a different story. It tells us that the black hole is also a giver, albeit a very slow one. The radiation it emits is thermal. This means it has a specific spectrum, like the glow of a hot piece of iron. or the light from a distant star. If we could isolate a black hole from all other noise in the universe, we would see this faint, uniform glow emanating from the horizon. It is the signature of the vacuum being torn apart by gravity. The challenge for scientists today is that this signal is almost impossible to detect. The Hawking radiation from an astrophysical black hole is so weak that it is effectively invisible against the background noise of the cosmos. We cannot yet build a detector sensitive enough to see it, nor can we travel close enough to a black hole to measure its temperature without being consumed by it. And yet, we rely on this theory because it connects the dots. It explains why black holes must have entropy, a measure of disorder. For years, physicists wondered if black holes had entropy. If they didn't, then dumping matter into one would be a way to decrease the total entropy of the universe, which violates the second law of thermodynamics. By proving that black holes radiate, Hawking proved that they have a temperature. And if they have a temperature, they must have entropy. The entropy is proportional to the surface area of the event horizon. This was a revolutionary insight. It suggested that all the information about what fell into the black hole is somehow encoded on the two-dimensional surface of the horizon, rather than being stored in the three-dimensional volume inside. This idea, the holographic principle, suggests that our entire understanding of space and volume might be an illusion, and that the true description of the universe exists on its boundaries. All of this stems from a few pages of calculations about virtual particles at the edge of a void. As we drift further into the silence of space, we can imagine these invisible processes happening across billions of galaxies. In every galactic center, a giant is slowly leaking. The event horizons are shrinking by fractions of a millimeter over millions of years. It is a process so slow that it feels like eternity, yet it is an inevitable march toward nothingness. The black hole, which we once thought was the ultimate destination of matter, is actually just a temporary storage facility. Everything it takes, the gas, the dust, the light of swallowed stars, is eventually processed through the quantum machinery of the horizon and leaked back into the void. But as this happens, the paradox deepens. If the radiation is truly thermal and random, the information that went in is not being returned, it is being erased. This would mean that the laws of physics are not reversible. It would mean that the past can be truly deleted from the universe. This is why the scientific community continues to debate Hawking's findings even decades later. They are not debating whether the radiation exists. The math is too elegant for that. But they are debating what it means for the nature of reality. Is the information preserved in some subtle correlation within the radiation? Does it leave a remnant behind at the very end? Or does the universe simply forget? We find ourselves standing at the edge of the known, looking into a darkness that is not quite as dark as we thought. The black hole is not a dead end. It is a transition. It is a place where gravity becomes so strong that it forces the quantum vacuum to reveal its secrets. As we move through this curved space-time, we realize that the event horizon is not just a border of doom. It is a window into the unification of physics. It is the only place in the universe where the very large and the very small are forced to interact. In the quiet leak of Hawking radiation, we find the first clues toward a theory of quantum gravity, a way to finally understand how the fabric of space and time is woven. Until that day comes, the black holes continue their slow evaporation. They sit in the centers of galaxies, surrounded by swirling disks of fire, while at their edges, invisible particles slip away into the night. The abyss is breathing. It is losing its grip on the matter it stole eons ago. One particle at a time, the most powerful objects in existence are fading away, returning their energy to a universe that will one day be cold, dark, and empty of everything but the ghost of what once was. To understand how this leakage occurs, we must first look at the vacuum of space, which is far from empty. In our everyday experience, a vacuum is simply a place where there is nothing. But in the realm of quantum mechanics, the vacuum is a sea of activity. It is alive with fluctuations, a shimmering field of energy that constantly gives birth to pairs of virtual particles. These are not particles in the traditional sense, but temporary disturbances in the underlying quantum fields. They appear as a particle and an antiparticle, popping into existence for a fraction of a second before they find each other and annihilate, returning their energy back to the void. This process happens everywhere, in every cubic centimeter of the universe, billions of times every second. Under normal circumstances, these pairs are invisible to us because they vanish almost as soon as they appear. They are like ghosts that haunt the fabric of spacetime, leaving no trace of their existence. However, the environment near a black hole is not normal. The curvature of space is so extreme that it begins to interfere with the very behavior of these quantum fluctuations. When a pair of virtual particles emerges exactly at the edge of the event horizon, they find themselves in a region of violent gravitational tension. Before they can reunite and annihilate, the tidal forces of the black hole can pull them apart. One particle is swept across the threshold, falling into the abyss where it can never return. The other particle, however, finds itself on the outside, stranded in the space just beyond the horizon. Without its partner to annihilate with, this second particle becomes a real particle. It is no longer virtual. It has acquired energy and mass from the gravitational field of the black hole. To an outside observer, it looks as though the black hole has emitted a particle of light or matter. This is the essence of Hawking radiation. The black hole is not pushing these particles out with some internal force. Instead, the geometry of space-time is ripping the vacuum apart and stealing one half of every pair that dares to form on its border. But energy cannot be created from nothing. The particle that escapes carries away a small amount of energy. And according to the most fundamental law of physics, that energy must come from somewhere. It comes from the black hole itself. Each escaping particle reduces the total mass energy of the black hole. This is why we say the black hole is evaporating. It is paying for the creation of these particles with its own substance. The process is a slow, relentless tax on the existence of the most massive objects in the cosmos. As we drift closer to this phenomenon, we can visualize the event horizon not as a wall, but as a semi-permeable membrane. On one side, gravity is so absolute that light itself is trapped. On the other side, there is a thin region where quantum effects begin to override the classical rules of relativity. In this narrow corridor, the black hole begins to bleed. It is a leak that operates on a scale so small, it defies human intuition. The particles being emitted are mostly photons and neutrinos, the lightest messengers of the universe. They drift away from the horizon in all directions, creating a faint thermal glow. This radiation is not like the blinding light of an accretion disk or the violent beams of a relativistic jet. Those phenomena happen far outside the horizon, driven by friction and magnetic fields as gas spirals inward. Hawking radiation is different. It originates at the very edge of the void, born from the vacuum itself. How does this process change as the black hole evolves over time? The answer lies in the relationship between mass and temperature. For most of its life, a stellar mass black hole is incredibly cold. Its temperature is far below that of the cosmic microwave background radiation that fills the entire universe. This means that for billions of years, a black hole actually absorbs more energy from the surrounding space than it emits through Hawking radiation. It is growing faster than it can evaporate. But this is a temporary state of affairs. The universe is expanding, and as it expands, the background radiation is cooling down. Eventually, the universe will become colder than the black hole. When that moment arrives, the balance shifts. The black hole will begin to lose more energy than it gains. This marks the beginning of its true decline. The thermal spectrum of this radiation reveals a strange inverse logic. In our world, larger objects often hold more heat or radiate more total energy, but in the quantum gravity of a black hole, size is a shield against evaporation. A supermassive black hole, such as the one at the center of our own Milky Way, has a mass millions of times that of our Sun. Because its event horizon is so vast, the curvature at the edge is actually relatively gentle compared to a smaller hole. This lower curvature means it creates fewer particle pairs and radiates very little energy. Its temperature is nearly absolute zero. For such a giant, the process of evaporation is an afterthought, a whisper in a storm of cosmic noise. But if we imagine a primordial black hole, one created in the high-density chaos of the Big Bang with the mass of a small asteroid, the story changes completely. A smaller black hole has a much tighter curvature at its horizon. The gravitational gradient is steeper, more violent. This intensity rips virtual particles apart with far greater frequency and energy. Consequently, small black holes are incredibly hot. They do not whisper, they scream in high-energy gamma rays. As a small black hole radiates, it loses mass. And as it loses mass, it becomes even smaller. Because temperature is inversely proportional to mass, the loss of mass causes the temperature to rise. This creates a runaway feedback loop. The hotter the black hole gets, the faster it radiates. The faster it radiates, the more mass it loses. And the more mass it loses, the hotter it becomes. This acceleration continues until the final moments of the black hole's life. In its last few seconds, a small black hole would release an amount of energy equivalent to millions of nuclear bombs, ending its existence in a brilliant flash of radiation that signals its total disappearance from the space-time manifold. For the massive black holes we observe today, however, this endgame is unimaginably distant. The timescale for a solar mass black hole to evaporate entirely is estimated to be around 10 to the power of 64 years. To grasp this number, we must first acknowledge that the current age of the universe is only about 13.8 billion years, which is roughly 10 to the power of 10. The time required for a black hole to vanish is not just longer than the history of our galaxy or the life of every star in the sky. It is so vast that the current age of the universe is a mere blink, an infinitesimal fraction of the journey toward evaporation. In this era of deep time, all other structures will have long since faded. The stars will have exhausted their fuel and collapsed into white dwarfs, neutron stars, or black holes. The galaxies will have drifted apart until every single one is isolated in a void of absolute darkness. Only then will the slow leak of Hawking radiation become the dominant process in the cosmos. In this silent epoch, the black holes will be the only remaining lanterns in the dark, though their light will be so faint and red-shifted that it would be nearly impossible to perceive. They will sit as solitary monuments to a forgotten era of matter and light, slowly shrinking as they surrender their mass back to the vacuum from which it once came. As we contemplate this slow dissolution, we must distinguish between what is seen and what is calculated. When astronomers use telescopes to study black holes, they are not seeing Hawking radiation. The images of the M87, or Sagittarius A, show us the accretion disk, a swirling maelstrom of gas heated to millions of degrees by friction and gravity. This light is classical. It is the result of matter falling in. It is a noisy, chaotic process that masks the subtle quantum leakage happening at the horizon. The jets of plasma shooting out from the poles of some black holes are also not Hawking radiation. Those jets are powered by the rotation of the black hole and the twisting of magnetic fields outside the event horizon. They are matter being flung away before it ever crosses the point of no return. Hawking radiation, by contrast, is a property of the horizon itself. It does not require an accretion disk to exist. Even a completely isolated black hole in a perfect vacuum will radiate. This is what makes the theory so profound. It suggests that the event horizon is not a static boundary, but a dynamic one. The very act of existing as a black hole creates a slow leak that ensures no object, no matter how massive or how hungry, can last forever. This brings us to the bridge between gravity and thermodynamics. For centuries, scientists viewed gravity as a geometric property of space and heat, as a statistical property of particles. They were separate worlds, but Hawking's discovery linked them. If a black hole has a temperature, it must have entropy. In physics, entropy is often described as disorder, but more accurately, it is a measure of the number of ways the internal components of a system can be arranged while keeping its overall appearance the same. For decades, it was assumed that black holes had zero entropy because they were so simple, described only by their mass, charge, and spin. This led to a crisis in physics. If you threw a high-entropy object, like a cloud of hot gas, into a black hole, the entropy of the universe would seem to decrease, which is forbidden by the second law of thermodynamics. Hawking radiation solved this problem. By showing that black holes radiate, he proved they have a temperature and therefore an entropy of their own. This entropy is not proportional to the volume inside the black hole, but to the surface area of its event horizon. This discovery shifted our entire perspective on information. It implies that everything a black hole swallows, the history of every star it consumed, the position of every atom it pulled in, is somehow recorded on the two-dimensional skin of the horizon. This leads us deeper into the physical mechanism of the shrink. As the black hole emits radiation, its total energy decreases. Because mass and energy are equivalent, as defined by Einstein's most famous equation, the loss of energy is a literal loss of mass. The event horizon, which is defined by the amount of mass contained within it, must respond to this change. It begins to contract. This is not a sudden collapse, but a microscopic receding of the boundary. For a supermassive black hole, this contraction is so slow that for all practical purposes, the horizon remains stationary. But over trillions upon trillions of years, the circle tightens. The void grows smaller. As the horizon shrinks, the gravitational gradient at the edge becomes steeper. This increase in curvature accelerates the production of virtual particle pairs. The radiation becomes more energetic, and the temperature rises. The black hole enters a phase of accelerating decay. It is as if the black hole is a candle that burns faster and hotter as it gets shorter. We can imagine this process as a cosmic recycling program. The matter that fell in was crushed into a state of extreme density, stripped of its identity, and hidden from the rest of the universe. But through Hawking radiation, that energy is slowly being returned to the cosmos. However, there is a catch. The radiation emitted is thermal. In physics, thermal radiation is random. It carries no specific pattern or signature of what created it. If you burn a library, the smoke and ash are thermal remnants. They do not contain the words of the books in any readable form. Similarly, if a black hole swallows a planet and then radiates that mass away as thermal photons, the information about the planet, its mountains, its oceans, its history, seems to be lost. This is where the physical process of evaporation crashes into the laws of quantum mechanics. The universe is supposed to have a perfect memory. Every state must be derivable from the state that came before it. But if the radiation is truly random, then the black hole has deleted a piece of the universe's history. This tension defines the current struggle in theoretical physics. We are forced to ask whether our understanding of gravity is incomplete, or if our understanding of quantum mechanics is flawed. Some theorists suggest that the radiation is not actually random, but contains subtle, encrypted correlations that preserve the information. Others propose that as the black hole reaches its final stage, it leaves behind a tiny, stable remnant, a microscopic seed that holds all the lost data. Still others suggest that the information is mirrored on the surface of the horizon in a way we cannot yet detect. Regardless of the answer, the physical reality remains: the black hole is leaking. It is an object defined by its ability to trap everything, yet it is doomed by a quantum glitch that allows a few particles to slip through. As we drift further into this contemplation, we can see the long-term architecture of the universe. We currently live in the stelliferous era, the age of stars. This is a time of abundance, where gas clouds collapse and ignite, filling the void with light. But the Hawking radiation calculations tell us about the era that comes after. Once the last star has burned out and the last white dwarf has cooled, we enter the black hole era. In this distant future, the only organized structures left in existence will be black holes. They will be the sole inheritors of the cosmos. For an incomprehensible amount of time, they will rule the void, drifting through a darkness so complete that there is no one left to observe them. But even they are not permanent. One by one, these titans will succumb to their own quantum nature. The smallest ones will vanish first, ending in bursts of light that illuminate the empty space for a fleeting moment before returning to blackness. Then, the stellar mass holes will follow, and finally, the supermassive giants will evaporate. The scale of this timeline is the ultimate exercise in humility. We measure our lives in decades, our civilizations in millennia, and our planet's history in billions of years. But the evaporation of a black hole operates on a scale that makes a billion years look like a nanosecond. It is a process of such profound patience that it renders all other events irrelevant. The rise and fall of every empire, the birth and death of every star, the collision of entire galaxies. All of these are merely preludes to the slow, quiet leak of the event horizon. When the final black hole finally evaporates, the universe will have reached a state of maximum entropy. There will be no more gradients of energy, no more heat, and no more structure. Only a thin, cold gas of photons and leptons will remain, spread so thinly across an infinite expanse that they will almost never meet. This is the theoretical end state of a universe governed by Hawking radiation, a total and absolute silence. But before that end, there is the transition. There is the long, slow journey from a singularity of infinite density to a cloud of vanishing particles. In this process, we find a strange symmetry. The black hole began as a collapse, a sudden, violent concentration of matter into a single point. Its death is the opposite, a gradual, ethereal diffusion of energy back into the void. It is the universe's way of correcting an imbalance. Gravity tried to lock matter away forever, but quantum mechanics found a loophole. The leak is the escape hatch. As we move through this conceptual space, we can feel the weight of that paradox. We are talking about objects that can swallow entire solar systems, yet their fate is decided by particles that exist for less than a trillionth of a second. It is a reminder that in the cosmos, the smallest things often dictate the destiny of the largest. The virtual particle, the flickering ghost of the vacuum, is the only thing capable of defeating a black hole. This realization changes how we view the darkness. The black hole is no longer just a grave. It is a slow-motion explosion. It is a transformation of matter into light, occurring over timescales that exceed our ability to imagine. The event horizon, which once seemed like the ultimate wall, is actually a filter. It allows nothing in to leave, but it allows the vacuum itself to breathe. The radiation escaping the horizon is the breath of the black hole, a slow exhale that lasts for eons. This process ensures that no matter how much a black hole consumes, it cannot keep its spoils forever. Everything borrowed from the universe must eventually be returned. The gold of accretion disks and the fire of quasars are just temporary displays of power. Underneath it all, the quantum leak is working, steadily eroding the foundation of the abyss. In the quietness of this realization, we can almost hear the ticking of that cosmic clock. Every black hole in every galaxy is slowly losing its grip. The massive centers of galactic clusters are shrinking by an amount so small it cannot be measured. But it is happening. The laws of physics have decreed that nothing, not even a singularity, is exempt from the passage of time and the increase of entropy. The void is not static, it is evaporating. We are living in the brief window where black holes seem eternal, but we are merely seeing them in their youth. In the deep future, they will be known as the things that vanished. The physical journey from the event horizon to the final flash of evaporation is a story of inevitable loss, but it is also a story of connection. It connects the smallest possible scale, the Planck length and quantum fluctuations, to the largest possible scale, the death of the universe. It shows us that gravity and quantum mechanics, though they seem to speak different languages, are describing the same reality. The Hawking radiation is the translation. It is the evidence that there is a deeper law, a more fundamental unity that governs both the falling star and the virtual particle. As we drift further into the void, we can imagine the silence of those distant horizons. We see the curvature of space as a gentle slope, leading not to a dead end, but to a slow release. The particles slipping away from the horizon are like memories escaping a dream. They carry with them the energy of a lost world, drifting through the darkness toward an infinite distance. This is the quiet destiny of all mass that falls into the dark. It is not destroyed. It is transformed. It is leaked back into the night, one photon at a time, until the last trace of the black hole is gone and the universe is finally, perfectly still. The scale of this countdown is almost impossible to hold in the mind. For a black hole with the mass of our sun, the evaporation process does not take millions or billions of years, but roughly 10 to the power of 64 years. To visualize such a number is to move beyond the boundaries of human intuition. If we were to represent the current age of the universe as a single second, the time it would take for a solar mass black hole to vanish would still exceed the lifespan of every star currently shining in every galaxy across the observable horizon. It is a duration that renders the concept of eternity almost tangible. In this time frame, the universe itself becomes a ghost town. The galaxies we see today will have drifted so far apart that they will disappear from each other's view, leaving every black hole as a lonely island in an ocean of absolute darkness. This slow decay creates a strange hierarchy of survival. Because Hawking temperature decreases as mass increases, the largest black holes are the coldest and most patient. The supermassive giants at the centers of galaxies, millions or billions of times the mass of our sun, are practically frozen. Their radiation is so faint that it is drowned out by the cosmic microwave background, the lingering heat from the Big Bang. For these titans, evaporation cannot even begin in earnest until the universe has cooled further than it is now. They are not yet leaking in any meaningful way because they are absorbing more energy from the background of space than they are emitting through quantum fluctuations. They are growing while the rest of the cosmos fades. But if we imagine a different kind of black hole, a primordial one, perhaps born from the extreme density of the very first moments after the Big Bang, the story changes. A black hole with the mass of a mountain would be vastly hotter than its stellar mass cousins. Its event horizon would be microscopic, and its gravitational gradient would be incredibly steep. For such an object, the quantum leak is not a slow drip, but a torrent. These small holes would evaporate rapidly, their temperature climbing as they shrink, eventually ending their lives in a violent explosion of high-energy gamma rays. While we have never detected such an event, the search for these primordial flashes remains a quiet obsession for astronomers. They look for the signature of a dying miniature void, a final scream of light that would signal the end of a microscopic titan. The relationship between mass and temperature is the engine of this process. In our everyday experience, we think of heat as something generated by friction or combustion. But in the vicinity of an event horizon, heat is a manifestation of geometry. The more curved the space-time, the more energetic the particles that escape. This creates a feedback loop of inevitable decline. As the black hole radiates energy, it loses mass. As it loses mass, its horizon shrinks, and the curvature becomes even more extreme. This increased curvature raises the temperature, which in turn increases the rate of radiation. The process is self-accelerating. For the first trillion years, the change is imperceptible. But as the mass reaches a critical threshold, the decay enters a runaway phase. We can imagine the researchers in their quiet offices, staring at these equations and feeling a sense of vertigo. There is a specific kind of silence that falls over a room when a mathematical result contradicts everything we thought we knew about reality. When Stephen Hawking first published his findings in 1974, the scientific community did not immediately embrace the idea. The notion that black holes could radiate was an affront to the classical definition of the event horizon. For decades, the horizon had been treated as the ultimate one-way street, a causal boundary where physics ended and nothingness began. To suggest that something could leak out was to suggest that the wall was porous. The resistance was not born of stubbornness, but of a deep respect for the laws of thermodynamics. If a black hole has a temperature, it must have entropy. But entropy is a measure of disorder, a count of the different ways the internal components of a system can be arranged. How could a black hole, an object that seems to consist of nothing but mass and gravity, have an internal arrangement? The classical view, known as the no-hair theorem, suggested that a stationary black hole is described by only three observable properties: its mass, its angular momentum, and its electric charge. Everything else, the chemical composition of the star it swallowed, the shape of the planets it crushed, was gone. It had no hair, no distinguishing features. This simplicity created a crisis. If a black hole is truly featureless, then its entropy should be zero. But if Hawking radiation exists, the laws of physics demand that the black hole possess an enormous amount of entropy. This contradiction forced a radical reimagining of what a horizon actually is. Physicists began to realize that the event horizon is not just a boundary in space, but a storage device. The area of the horizon became the key. They discovered that the entropy of a black hole is proportional to its surface area, not its volume. This was a revelation that shifted the entire paradigm of cosmology. It suggested that all the information about everything that ever fell into the black hole is not lost in the singularity, but is somehow encoded on the two-dimensional shell of the horizon. This leads us to one of the most profound and unsettling conflicts in modern science: the black hole information paradox. In quantum mechanics, there is a fundamental rule called unitarity. It states that information can never be truly destroyed. If you know the exact state of every particle in a system today, you should be able to mathematically reconstruct its state from yesterday. Information is the DNA of the universe. It is what makes a carbon atom different from an oxygen atom, and a star different from a cloud of dust. But Hawking's original calculation suggested that the radiation emitted during evaporation is purely thermal. It is random noise. If you throw a book into a black hole, and the black hole eventually evaporates into a cloud of random heat, where did the information in the book go? If the radiation carries no record of the book's contents, then the information has been deleted from the universe. This is not just a problem for librarians or historians. It is a catastrophe for physics. If information can be destroyed, then the laws of quantum mechanics are wrong. But if the information escapes, then our understanding of gravity and the speed of light must be flawed. Because nothing, not even information, is supposed to travel faster than light to escape from inside the horizon. The paradox creates a theoretical deadlock. On one side, we have general relativity, which tells us that once you cross the horizon, there is no way back. On the other side, we have quantum mechanics, which tells us that the universe never forgets. For years, these two pillars of science have been at war over the fate of a single particle. The tension is palpable in the theoretical papers and the late-night debates of physicists who realize they are staring at a crack in the foundation of reality. They are searching for a loophole, a way to reconcile the absolute nature of the horizon with the eternal nature of information. One proposed solution suggests that the radiation is not as random as it seems. Perhaps there are subtle correlations, microscopic patterns woven into the Hawking radiation like an invisible ink. In this view, the black hole doesn't just leak energy. It slowly leaks the history of everything it ever consumed, encoded in a form so complex that it looks like noise to any observer who doesn't have the key to decrypt it. This would mean that the information is not destroyed, but merely scrambled and radiated back into space over an unimaginable stretch of time. Another possibility is far more radical: the holographic principle. This theory proposes that our three-dimensional experience of the universe is actually a projection of information stored on a distant two-dimensional surface. In this framework, the event horizon is not a wall, but a screen. When an object falls into a black hole, its three-dimensional form is lost, but its information is smeared across the surface of the horizon like a hologram. As the black hole evaporates, it simply peels away layers of this holographic data and sends them back into the void. This would resolve the paradox by suggesting that nothing ever truly entered the black hole in the first place. It was merely recorded on the edge. Yet, these are theories born of mathematical necessity, not direct observation. The reality is that detecting Hawking radiation from a real astrophysical black hole is currently impossible. The radiation from a stellar mass black hole is far colder than the vacuum of space around it. To see it, we would need to find a black hole in a universe where everything else had already died. A void so cold and empty that the faint glow of evaporation became the brightest thing in existence. We are trapped in an era of too much light, too much heat, and too many stars to ever witness this process in real time. This invisibility makes the study of black hole leakage a journey of pure thought. It is science conducted in the mind's eye, using the language of tensors and quantum fields to probe a region of space that we can never visit and an event we can never see. There is something deeply human about this pursuit, the attempt to understand the end of all things through the logic of numbers. It is an exercise in intellectual courage to accept that the most massive objects in the universe are governed by the smallest, most fleeting fluctuations of the vacuum. When we consider the balance of energy, we see that black holes are not the eternal tombs they were once thought to be. They are temporary reservoirs. Every bit of matter they steal from a star or a gas cloud is eventually earmarked for return. The accretion disks we observe, the swirling rings of fire and gold that surround supermassive black holes, are just the intake valves. The Hawking radiation is the exhaust. One is violent, fast, and visible. The other is quiet, slow, and invisible. But together, they form a complete cycle of cosmic metabolism. The transition from an absorbing object to an evaporating one marks the beginning of the end for the black hole's dominance. For eons, gravity was the undisputed king, pulling everything toward a single point of no return. But in the long game, quantum mechanics wins. The vacuum itself, with its restless energy and virtual particles, slowly eats away at the horizon. It is a war of attrition where the enemy is the very fabric of space. As we contemplate this, we can imagine the slow shift in the cosmic landscape. We move from a universe of structure, galaxies, nebulae, and planets, to a universe of voids. The black holes will be the last lanterns in the dark, their faint glow marking the places where worlds once existed. They will shrink with an agonizing slowness, their horizons drawing inward, tightening like a closing eye. Each photon that escapes is a tiny victory for the laws of thermodynamics, a small piece of order being traded for a larger amount of disorder. The information paradox remains an open wound in physics because it forces us to choose which law to break. If we save quantum mechanics, we must rethink gravity. If we save relativity, we must accept that the universe can forget. This uncertainty is where the most exciting science happens. It is the boundary where our current maps end and the territory of a new theory, perhaps a theory of quantum gravity, begins. The leak in the black hole is not just a physical process, it is a clue. It is the universe telling us that there is a deeper layer of reality we have not yet reached. We can feel the weight of this silence as we drift through the conceptual void. We are thinking about timescales that dwarf the life of our sun, and sizes that shrink below the Planck length. The black hole, once the symbol of absolute power and inevitable destruction, is revealed to be fragile. It is subject to the same laws of decay as a dying leaf or a cooling ember. Its only difference is the scale of its patience. In this slow evaporation, there is a strange kind of peace. The violence of the collapse, the tearing apart of stars and the crushing of atoms, is eventually smoothed over by the gentle emission of radiation. The chaos of the singularity is slowly undone. The universe is not just expanding, it is cleaning itself. It is erasing the scars left by the deaths of massive stars, turning the concentrated darkness of black holes back into the diffused light of the vacuum. This process ensures that no single point in space can hold a monopoly on matter forever. The event horizon is a temporary lock, and Hawking radiation is the key that slowly turns. It tells us that the cosmos has a way of reclaiming everything it creates. Nothing is truly lost. It is only transformed, moved from one state to another, drifting from the center of a void back into the infinite expanse of the night. As we move further into this meditation, we can see the black holes not as monsters, but as cosmic clocks. Each one is counting down to its own disappearance. The supermassive ones are ticking slowly, their hands barely moving over billions of years. The smaller ones are racing toward their end. Together, they orchestrate the final act of the universe's biography. They are the custodians of the end times, holding on to the last remnants of matter and energy before releasing them into the great stillness. The radiation that escapes is a whisper from the abyss. It carries no voice, no message, and perhaps no memory, but it represents the ultimate liberation. To be radiated away as a photon is to be freed from the crushing grip of the singularity. It is to move from a place of infinite curvature back into the flat, open freedom of deep space. The particles that leak out are the only things that ever truly escape the dark. We find ourselves floating in this vision of the far future, where the last black holes are flickering like dying stars. The darkness is no longer oppressive. It is a canvas of absolute equilibrium. The tension between gravity and quantum mechanics has finally been resolved, not through a formula on a chalkboard, but through the physical exhaustion of the universe. Everything that was once concentrated has been spread thin. Everything that was hidden has been revealed as heat. The information paradox may never be solved by a human mind, for we are creatures of a brief and noisy era. But the universe solves it through the simple act of existing. Through the slow leak of the horizon, the cosmos balances its books. It settles its debts with gravity and pays them back in light. We are witnesses to this process only in theory, but the theory is our bridge to the end of time. In the quietness of this realization, the black hole ceases to be a place of terror. It becomes a symbol of transition. It is the bridge between the material world we know and the ethereal world of pure radiation. It is the final filter through which all matter must pass before it returns to the void. The leak is not a flaw in the system. It is the system working exactly as intended. As we drift further, we can imagine the very last black hole in existence, a tiny, shimmering speck of mass, radiating with an intensity that would blind any observer. It is the final concentrated point of energy in all of creation. And then, in a final flash of light, a sudden, silent explosion, it vanishes. The horizon closes for the last time. The leak is complete. The universe is now empty, but it is not void. It is filled with the ghosts of everything that ever was, spread so thinly across the expanse that they are indistinguishable from the darkness itself. The information is there, perhaps, in the subtle patterns of the remaining photons, a faded map of every galaxy and every heart that ever beat. But there is no one left to read it. There is only the stillness. This is the ultimate destination of the Hawking radiation journey. It takes us from the terrifying edge of an event horizon to the absolute peace of maximum entropy. It shows us that even the most powerful forces in nature are temporary. Even the darkness has a limit. The leak ensures that nothing stays hidden forever, and nothing remains trapped. We can feel the rhythm of this cosmic exhale. Inhale, the collapse of a star, the birth of a black hole, the gathering of mass. Exhale, the slow leak of radiation, the shrinking of the horizon, the return to the void. This is the breath of the universe, occurring over scales that make our entire history seem like a single heartbeat. We are living in the middle of the inhale, surrounded by the growth and fire of stars. But the exhale is inevitable. The beauty of this process lies in its impartiality. The black hole does not care what it swallows, whether it is a stray planet or a beam of light. And the radiation it emits does not care where it goes. It is a mechanical, mathematical certainty. It is the universe returning to its simplest state. As we float through this conceptual darkness, we can let go of the need for answers. The information paradox can remain a mystery. The final state of the singularity can remain hidden. All that matters is the movement. The slow, steady migration of energy from the dark back into the light. The leak is a promise that the universe will not end in a permanent prison, but in a complete and total release. We are drifting now, far beyond the reach of any galaxy, past the last flickering horizons of the dying voids. The space around us is cold, silent, and perfectly still. There is no more gravity to pull us, no more light to blind us. Only the memory of the leak remains, the knowledge that everything that fell into the dark eventually found its way back out. The journey from the event horizon to the end of time is a path of simplification. We strip away the complex structures of matter and energy until only the most fundamental truths remain. The truth that mass is energy, that space is curved, and that nothing, not even a black hole, can resist the slow erosion of quantum time. In this stillness, we can finally see the symmetry of it all. The universe began with a burst of radiation and expanded into structure. It ends by breaking down that structure and returning to radiation. The Hawking leak is the closing of the circle. It is the final step in a grand cosmic cycle that transforms everything from nothing and eventually returns everything to nothing. We are now just observers in this silent expanse, floating in the wake of the last evaporation. The void is no longer a place of hunger or danger. It is a place of rest. The black holes have all vanished, leaving behind a universe that is finally perfectly balanced. There are no more horizons to cross, no more boundaries to fear. The long, slow leak has finished its work. The energy has been distributed. The information has been scattered. The darkness is now complete. But it is a darkness of peace, not of loss. We have followed the path from the event horizon to the very end of existence. And we find that there is nothing left to fear. The silence is absolute. The void is full. The journey is over. The lingering question of what happens to the information that falls into a black hole is perhaps the most profound tension in modern physics. When we speak of information in this context, we are not referring to data in a book or memories in a mind, but to the fundamental quantum state of every particle that ever crossed the event horizon. In our current understanding of quantum mechanics, there is a principle called unitarity, which dictates that information can never be truly destroyed. If you know the exact state of a system at one moment, you should be able to calculate its past and its future with absolute certainty. The universe is supposed to keep a perfect ledger of every interaction, every collision, and every movement of every subatomic particle since the dawn of time. However, the classical view of a black hole suggests a total erasure. Once an object passes the event horizon, it is disconnected from our causal reality. It is gone, stripped of its identity, and crushed into a singularity where our laws of physics break down. For decades, this seemed acceptable because the information was simply hidden behind a door that could never be opened. We could live with the loss because the door was absolute. But Hawking radiation changed the nature of the problem by introducing an exit. If a black hole evaporates completely, and if that radiation is purely thermal, meaning it is random and carries no signature of what fell in, then the information is not just hidden. It is deleted from existence. This creates a paradox that threatens the very foundation of physics. If information can be destroyed, then the laws of quantum mechanics are incomplete. If information cannot be destroyed, then Hawking's original calculation must be missing something fundamental about how radiation carries data away from the horizon. We find ourselves in a conceptual deadlock where two of our most successful theories, general relativity and quantum field theory, are telling us opposite things about the fate of a single atom. How can the universe resolve this conflict? Some theorists suggest that the information is not lost, but is instead encoded on the surface of the event horizon itself. This leads to the holographic principle, a staggering idea that suggests the three-dimensional volume of a black hole is actually a projection of two-dimensional information stored on its boundary. In this view, everything that falls into the black hole is like a piece of data being written onto a cosmic hard drive at the edge of the void. As the black hole evaporates, the radiation carries this encoded information back out into the universe, though in a form so scrambled and distorted that it would be nearly impossible for any observer to reconstruct. The original object, a star, a planet, a stray cloud of gas, is not returned as a physical entity, but its quantum blueprint is leaked back into the vacuum, one photon at a time. Yet, this solution introduces another problem known as the firewall paradox. If information is being reflected or stored at the horizon to be radiated away later, it implies that the event horizon is not the smooth, empty space predicted by general relativity. Instead, it might be a high-energy barrier, a wall of fire that incinerates anything attempting to cross it. This would mean that an observer falling into a black hole would not drift peacefully across the boundary as Einstein's equations suggest, but would instead hit a violent ceiling of quantum energy and be destroyed instantly. The smooth descent is replaced by a sudden, catastrophic end. We are forced to choose between three deeply held beliefs: that information is preserved, that general relativity is correct about the nature of the horizon, or that quantum field theory holds true in curved spacetime. We cannot keep all three. One of them must be wrong. The room where these discussions happen often goes very quiet when this realization sets in, because it means our map of reality has a fundamental hole in it. The black hole is no longer just an object of study. It has become the laboratory where we are forced to confront the limits of human logic. The difficulty of resolving this paradox is compounded by the fact that we cannot simply go and check. To observe Hawking radiation directly from an astrophysical black hole would require a level of sensitivity that is currently beyond our reach. The thermal radiation emitted by a solar mass black hole is incredibly faint, far colder than the cosmic microwave background radiation that fills the rest of the universe. In practice, most black holes in our current era are actually absorbing more energy from the background of space than they are leaking through Hawking radiation. They are growing, not shrinking, and the subtle whisper of their evaporation is drowned out by the roar of the surrounding cosmos. To detect a single photon of Hawking radiation would be like trying to hear a single pin drop in the middle of a hurricane. We can see the accretion disks, we can measure the gravitational waves from colliding horizons, and we can photograph the shadow cast against the glowing gas of a galactic center. But the evaporation remains a theoretical ghost. It is a prediction derived from the elegant marriage of mathematics and physics, yet it remains hidden from our instruments. This creates a strange tension in the scientific community. We have a theory that is too beautiful to be wrong, but evidence that is too elusive to be confirmed. This lack of direct detection does not diminish the importance of the work. Instead, it pushes us toward more abstract ways of thinking about space and time. If the information paradox cannot be solved by looking at the radiation, perhaps the answer lies in the geometry of space-time itself. Some propose that black holes are connected by wormholes to other parts of the universe, or other universes entirely, allowing information to leak out through a hidden back door. Others suggest that the singularity does not exist at all, and that matter reaches a certain density before bouncing back in a process that reverses the collapse over trillions of years. Each proposal is an attempt to save the principle of unitarity, to ensure that the universe never forgets. But as we weigh these options, we must acknowledge the possibility that our intuition about information is simply incorrect. Perhaps the universe does forget. Perhaps there are processes in the heart of a black hole that permanently erase the history of matter, leaving behind a blank slate. If this were true, it would mean that the past is not permanently etched into the fabric of existence, but can be deleted by gravity. We move through these theories as if we are navigating a fog, where each new calculation provides a glimpse of a landmark before it vanishes again. The struggle to understand the black hole information paradox is a struggle to understand the nature of reality itself. Is the universe a holographic projection? Is space-time an emergent property of quantum entanglement? These questions, which seem like science fiction, are the direct result of trying to figure out why a black hole leaks. The implications extend far beyond the edge of a distant void. If space and time can be manipulated or erased by a black hole, then our entire perception of linear time may be an illusion. The process of evaporation suggests that the end of a black hole is linked to its beginning in a way that defies our standard experience of cause and effect. We are looking at a system where the final state, the total disappearance of the mass, might actually determine how the information was stored at the very start. We can imagine the frustration of the physicists who spent their lives chasing these answers, only to find that the more they learned, the less certain they became. There is a specific kind of humility that comes with studying black holes. It is the realization that there are places in the universe where our most trusted tools simply stop working. The mathematics begin to return infinities, the geometry twists into knots, and the logic of before and after ceases to have meaning. As we drift further into this conceptual space, we realize that the silence of the black hole is not an absence of information, but a saturation of it. The horizon is not just a border. It is a library containing everything the black hole has ever consumed. Every atom of every star, every photon from every distant galaxy, and every piece of dust that ever crossed that line is recorded there. The Hawking radiation is the slow process of reading that library, one letter at a time, over an incomprehensible stretch of eons. But the letters are scrambled. The language of the radiation is not the language of the objects that fell in. A star does not come out as a star. It comes out as a chaotic spray of thermal particles. To reconstruct the star from the radiation would require a computer larger than the universe and a time frame longer than the life of all galaxies. For all practical purposes, the information is lost, even if it is technically preserved. This distinction between theoretical preservation and practical recovery is where the mystery truly lives. We are forced to consider that the universe may have a built-in mechanism for forgetting. While quantum mechanics forbids the destruction of information, gravity seems determined to hide it so effectively that the difference becomes meaningless. The black hole acts as a cosmic shredder, turning structured matter into random noise. Even if the shreds still exist, the original document is gone forever. This leads us to a place of deep contemplation regarding the scale of the cosmos. We spend our lives measuring seconds and years, while the evaporation of a black hole measures its progress in powers of 10 that defy human language. A solar mass black hole takes 10 to the 64th power of years to vanish. To put that number in perspective, the current age of the universe is only about 13.8 billion years, a mere blink compared to the patience of a leaking horizon. In this vast timeline, the information paradox becomes a slow-motion drama. The conflict between relativity and quantum mechanics plays out over durations so long that the stars themselves will have long since gone cold. The galaxies will have drifted apart until every observer is alone in an infinite dark. Only then, in the ultimate solitude of the deep future, will the black holes begin to dominate the landscape. They will be the last remaining structures in a universe of cooling gas and drifting photons. The radiation they emit will be the only light left in existence. This faint, thermal glow is the final testament to everything that ever happened. The history of every civilization, the birth of every sun, and the collapse of every nebula are all contained within that leaking energy. We are looking at the ultimate archive of the universe, written in a code that no one will ever be able to decrypt. The limits of our evidence are the boundaries of our current existence. We cannot see the radiation because we are too early. We are living in the era of light and heat, where the noise of creation drowns out the whisper of decay. To truly witness Hawking radiation, we would have to travel billions of years into the future, past the death of the last star, to a time when the universe is cold enough for the leak to become visible. Until then, we rely on the mathematics. We trust in the consistency of the equations that tell us black holes must evaporate. This trust is a form of scientific faith, a belief that the laws of physics are universal and that they apply even in the most extreme environments imaginable. The fact that Hawking radiation has not been detected does not mean it isn't happening. It simply means we are small and our time is short. We can feel the weight of this realization as we float through the void. We are creatures of a brief moment, trying to understand a process that spans the entire lifespan of the cosmos. The information paradox is not just a puzzle for physicists to solve. It is a reminder of our place in the grand architecture of space and time. We are observers on the shore of an ocean we can barely describe, watching waves that take trillions of years to break. The beauty of this mystery lies in its refusal to be easily solved. If we had the answer today, the black hole would become just another object in a catalog. But because it remains a paradox, it continues to pull at us, forcing us to rethink everything we know about gravity and light. It pushes us toward a more unified theory, a way of seeing the universe where the very small and the very large are finally reconciled. We drift now through the implications of this reconciliation. We imagine a universe where information is never lost, but always transformed, where every particle that falls into the dark eventually returns to the light, albeit in a form we cannot recognize. The leak in the black hole is the mechanism of this transformation. It is the process by which the universe recycles its most concentrated forms of energy back into the void. The event horizon, once thought to be an eternal prison, is revealed as a temporary filter. It holds onto the matter for a while, stripping it of its form and its history, before slowly releasing it back into the expanse. This suggests that the universe has a way of balancing itself, a cosmic accounting system that ensures nothing is truly deleted, only redistributed. As we move further away from the event horizon in our mind's eye, we see the black hole not as a void, but as a slow-burning candle. It consumes everything in its path, but it also gives back, however slowly. The radiation is the breath of the black hole, a long and steady exhale that will eventually empty the cosmos of all concentrated mass. We are floating in the wake of this realization. The paradoxes, the firewalls, and the holographic projections are all attempts to describe a reality that is far more complex than our senses can perceive. We are trying to map the invisible using tools made of light and matter, but the black hole teaches us that light and matter are just temporary states of something deeper. The information paradox remains an open wound in physics, but it is a productive wound. It is the gap through which new ideas enter. It is the reason we continue to look at the darkness and ask why. The silence of the event horizon is not empty. It is pregnant with the possibility of a new understanding. Every calculation that fails to solve the paradox brings us one step closer to the theory that will finally explain how gravity and quantum mechanics coexist. We drift now in the quietude of this uncertainty. There is a strange comfort in knowing that there are still mysteries that cannot be solved by a simple equation. The black hole remains the ultimate secret, a place where the universe hides its most precious data behind a veil of curved spacetime. We can speculate about the nature of the radiation and the fate of the information, but for now, we must accept the silence. The leak continues, unseen and unheard, across the vast reaches of space. It is the slowest process in existence, yet it is the most inevitable. Every black hole in every galaxy is currently losing mass, one infinitesimal particle at a time. The countdown has already begun. The ledger is being balanced. The universe is slowly erasing its most extreme concentrations of power, returning everything to the equilibrium of the void. We are witnesses to this process through the lens of theory, drifting along the currents of thought that lead us from the edge of a singularity to the end of time. We have seen how the certainty of the one-way horizon was dismantled by the quantum leak, and how that leak created a paradox that challenges our understanding of existence itself. The black hole is not just a grave for stars. It is a crucible where the laws of nature are tested and refined. As we move deeper into this stillness, we let the complexities of the information paradox fade into the background. We no longer need to solve the equation. We only need to feel the scale of it, the immense patience of the evaporating black hole, the fragility of a singularity that can be erased by its own radiation, and the possibility that every piece of us is eventually returned to the stars in a form we cannot imagine. The void around us is no longer a place of loss. It is a place of transition. We are floating in a sea of potential information, where the ghosts of dead galaxies are being whispered back into existence by the Hawking radiation. The universe is not ending. It is unfolding, revealing its final state as a perfect, featureless expanse of light and shadow. We drift further still, leaving behind the noise of the paradoxes and the tension of the theories. We enter a state of pure observation, where the black hole is simply a point of transition in an infinite cycle. The leak is the bridge, the radiation is the path, and we are the travelers, floating through the conceptual dark toward a peace that exceeds all understanding. The cosmic clock ticks in a rhythm that dwarfs all human experience, moving toward an era where the black hole is the only remaining actor on the stage of existence. In this remote future, the universe has expanded so far that galaxies are no longer visible to one another. The light from distant clusters has shifted beyond the reach of any detector, leaving every observer in a private bubble of absolute dark. Within this solitude, the evaporation process accelerates. As a black hole loses mass through its steady leak of radiation, it becomes smaller and hotter. This is the strange inversion of cosmic thermodynamics. While a star cools as it dies, a black hole grows more energetic as it vanishes. The shrinking horizon becomes a focal point of increasing intensity, a tiny spark in an infinite ocean of cold. We imagine this final phase not as a violent explosion, but as a gradual brightening. The radiation that was once an undetectable whisper becomes a steady hum, then a glow, and finally, a flash of pure energy. When the mass of the black hole reaches its final infinitesimal stage, the remaining energy is released in a sudden burst of particles, leaving behind nothing but a void where a giant once stood. This is the ultimate dissolution. The singularity, which had curved space-time into an impossible knot for eons, simply unravels. The tension that held the fabric of the universe tight around it relaxes. The curvature flattens. The space where gravity once reigned supreme becomes indistinguishable from the empty vacuum surrounding it. This process represents the final accounting of the cosmos. Every atom that ever fell into the dark, every photon captured by the event horizon, has been processed through this quantum filter and return to the expanse. Whether that return preserves the memory of what was lost remains a question for a physics we have yet to master, but the physical energy is restored. The universe returns to a state of maximum entropy, a perfect equilibrium where no more work can be performed and no more structures can form. It is the great stillness, a peace so profound that time itself ceases to have meaning. There are no longer any clocks to measure, for there are no longer any changes to observe. We drift now away from these distant horizons, pulling back from the edge of the end of time. We leave behind the evaporating giants and the ghosts of vanished galaxies. The scale begins to shift, moving from the incomprehensible reaches of the deep future back toward the familiar coordinates of the present. We glide past the great voids and the filaments of dark matter, sliding through the layers of cosmic history in reverse. The universe begins to warm again as we move backward through the eons. The first stars reignite in our wake, their blue-white light piercing the primordial gloom. Galaxies coalesce from clouds of hydrogen and helium, spinning into the great spirals that populate our night sky. We move closer still, entering the local neighborhood of a single yellow dwarf star. We feel the gentle pull of its gravity, a welcoming force that guides us home. The vastness of the interstellar medium gives way to the warmth of a solar system. We pass the frozen sentinels of the Oort cloud and the jagged remnants of the asteroid belt. The scale of our perception narrows from billions of light years to millions of miles, then thousands, until we are floating in the thin, blue atmosphere of a small, vibrant world. The noise of the cosmos fades into the background, replaced by the soft, rhythmic sounds of a living planet. We feel the weight of gravity not as a crushing force of a singularity, but as a gentle anchor holding us to the Earth. The terrifying beauty of the black hole is now only a thought, a distant mathematical truth that exists far beyond our reach. The paradoxes and the radiation are merely stories we tell ourselves to understand the infinite, while the reality of this moment is found in the coolness of the air and the stillness of the room. The darkness outside the window is no longer a void to be feared or a mystery to be solved. It is simply the night. The stars that twinkle above are not distant furnaces or precursors to collapse, but quiet companions in a vast and silent dance. We let go of the need to know the final answer to the information paradox. We accept that some secrets are meant to stay hidden behind the horizon, protected by the laws of physics until the end of time. There is a profound relief in this surrender, a sense of belonging to a universe that is far larger and more mysterious than our minds can ever fully grasp. The mind begins to settle, mirroring the equilibrium of the deep cosmos. The thoughts that raced through quantum fields and curved spacetime now slow down, drifting like dust motes in a beam of moonlight. The tension of discovery gives way to the comfort of existence. We are small, yes, but we are part of this architecture. Every atom in our bodies was once forged in the heart of a star, and every thought we think is a ripple in the same fabric that Hawking radiation slowly unravels. We are made of the same stuff as the black holes and the nebulae, connected by an invisible thread of energy and information that spans the entire history of everything. The breath becomes slow and deep, synchronizing with the pulse of the Earth. The room is a sanctuary, a small pocket of warmth in the infinite cold. The blankets are heavy and secure, providing a tactile certainty that outweighs any theoretical uncertainty. The sounds of the world outside, the distant hum of traffic, or the rustle of wind through leaves, become a lullaby, grounding us in the here and now. We are safe. We are home. The journey is complete. We have traveled to the edge of existence and back again, crossing boundaries that light itself cannot breach. We have seen the slow death of giants and the birth of new understandings. Now, we leave those visions behind, letting them dissolve into the soft haze of sleep. The equations fade. The horizons vanish. The radiation ceases its whisper. The universe is vast, but this room is enough. The cosmos is ancient, but this moment is current. The void is deep, but the bed is warm. The dark is absolute, but the mind is at peace. The stars are distant, but the breath is near. The mystery is eternal, but the night is here. We sink further into the softness of the pillows, feeling the body become weightless, as if floating once more in the quiet currents of space, but without the fear of the fall. There is no pull now, only a gentle drift toward unconsciousness. The mind closes its eyes to the light of distant quasars and opens them to the inner landscape of dreams. The silence is complete. The stillness is absolute. The heart beats in time with the cooling universe. The spirit rests in the cradle of the night. The long voyage ends in a soft exhale. The Tehit cosmic drift settles into a deep, dreamless slumber. Sleep well tonight.